Electrical engineering encompasses a wide range of principles and applications. Let's explore some frequently asked questions to enhance understanding of key electrical concepts. Firstly, consider the fundamental laws governing electrical circuits. Ohm's law, expressed as volts equals current times resistance, describes the relationship between voltage, current, and resistance in a circuit. Understanding this law is crucial for analyzing and designing electrical circuits. Secondly, Kirchhoff's laws provide additional tools for circuit analysis. Kirchhoff's current law, or KCL, states that the total current entering a junction must equal the total current leaving the junction. Kirchhoff's voltage law, or KVL, states that the sum of the voltages around any closed loop in a circuit must equal zero. These laws are essential for solving complex circuit problems. Thirdly, consider the concept of electrical power. Power, measured in watts, is the rate at which electrical energy is transferred in a circuit. Power can be calculated as the product of voltage and current, or P equals volts times amps. Understanding power calculations is vital for determining the energy consumption and efficiency of electrical devices. Next, let's discuss alternating current or AC and direct current or DC. Direct current flows in one direction only, while alternating current periodically reverses direction. The frequency of AC, measured in Hertz, indicates the number of complete cycles per second. In the United States, the standard AC frequency is 60 Hz. Alternating current is typically used for power distribution due to its ability to be efficiently transmitted over long distances using transformers. Transformers are devices that can step up or step down voltage levels in AC circuits. They operate based on the principle of electromagnetic induction, where a changing magnetic field induces a voltage in a nearby coil. Transformers are essential components in power transmission and distribution systems. Now let's examine electrical safety. Electrical safety is of paramount importance to prevent electrical shocks, fires, and other hazards. Grounding is a crucial safety measure that provides a low resistance path for fault currents to flow back to the source, tripping a circuit breaker or fuse and disconnecting the circuit. Ground fault circuit interrupters, or GFCIs, are designed to detect small ground faults and quickly interrupt the circuit, protecting individuals from electrical shock. Arc fault circuit interrupters, or ASIs, are designed to detect arc faults, which are dangerous electrical discharges that can cause fires. Consider the National Electrical Code, or NEC, which provides comprehensive guidelines for safe electrical installations. The NEC is a widely adopted standard that outlines requirements for wiring methods, overcurrent protection, grounding, and other aspects of electrical systems. Compliance with the NEC is essential to ensure the safety and reliability of electrical installations. Article 210.12 addresses arc fault circuit interrupter protection. Article 250 covers grounding and bonding. Article 300 addresses wiring methods. Table 310.15b16 addresses ampacities of insulated conductors. Let's delve into the topic of electrical motors. Electrical motors convert electrical energy into mechanical energy. There are various types of electrical motors, including AC motors, DC motors, and servo motors. AC motors are commonly used in industrial applications due to their robustness and efficiency. DC motors are often used in applications where precise speed control is required. Servo motors are used in applications where precise position control is needed. The torque and speed characteristics of an electrical motor are important factors to consider when selecting a motor for a particular application. Then there's the subject of programmable logic controllers, or PLCs, which are used extensively in industrial automation. PLC are specialized computers that control industrial processes based on programmed logic. They receive input signals from sensors, process the signals according to the programmed logic, and generate output signals to control actuators. PLC are highly reliable and flexible, making them ideal for a wide range of industrial applications. Regarding power distribution systems, these systems deliver electrical power from the source to various loads. Power distribution systems typically consist of transformers, switchgear, protective devices, and conductors. The design of a power distribution system must consider factors such as voltage drop, fault current, and reliability. Redundancy is often incorporated into power distribution systems to improve reliability and ensure continuous operation. Next, we can discuss renewable energy sources, such as solar power and wind power, which are becoming increasingly important in the transition to a sustainable energy future. Solar power utilizes photovoltaic cells to convert sunlight directly into electricity. Wind power utilizes wind turbines to convert wind energy into electricity. Renewable energy sources offer the potential to reduce reliance on fossil fuels and mitigate climate change. In the realm of electrical measurements, various instruments are used to measure electrical quantities. Voltmeters measure voltage, ammeters measure current, and ohmmeters measure resistance. Multimeters combine these functions into a single instrument. Oscilloscopes are used to visualize electrical waveforms and analyze circuit behavior. Power quality analyzers are used to measure and analyze various power quality parameters such as voltage sags, voltage swells, and harmonics. Now consider electrical drawings and diagrams, which are essential tools for designing, installing, and maintaining electrical systems. Single-line diagrams provide a simplified representation of a power system, showing the major components and their interconnections. Wiring diagrams show the detailed wiring connections between components. Schematic diagrams show the functional relationships between components. Then there is the topic of lighting systems. Lighting systems provide illumination for various spaces, including residential, commercial, and industrial environment. Different types of lighting technologies are available, including incandescent lamps, fluorescent lamps, and light-emitting diodes, or LEDs. LED are becoming increasingly popular due to their energy efficiency, long lifespan, and versatility. Regarding grounding and bonding, these are critical for electrical safety. Grounding provides a low-impedance path for fault currents to flow back to the source, tripping a circuit breaker or fuse and disconnecting the circuits. Bonding connects metallic parts of an electrical system together to equalize their potential, reducing the risk of electric shock. Proper grounding and bonding are essential for protecting people and equipment from electrical hazards. Also, consider surge protection. Surge protective devices, or SPDs, are used to protect electrical equipment from voltage surges caused by lightning strikes, power switching, and other transient events. SPD diverts surge currents to ground, preventing them from damaging sensitive electronic equipment. SPD are commonly installed at the service entrance of a building and at downstream locations to provide comprehensive surge protection. Another important area is harmonics. Harmonics are sinusoidal voltages or currents that are integer multiples of the fundamental frequency. Harmonics can cause various problems in electrical systems, including overheating of equipment, increased losses, and reduced power quality. Harmonic filters can be used to mitigate the effects of harmonics. In the area of power factor correction, power factor is a measure of how effectively electrical power is being used in a circuit. A low power factor indicates that a significant portion of the current is reactive and does not contribute to doing useful work. Power factor correction can be achieved by adding capacitors to the circuit to compensate for the reactive current. Improving the power factor can reduce energy losses and improve the efficiency of the electrical system. Another important consideration is motor control. Motor control involves starting, stopping, and controlling the speed and torque of electrical motors. Various types of motor starters are available, including across-the-line starters, reduced voltage starters, and variable frequency drives, or VFDs. VFD provide precise speed control and can significantly reduce energy consumption in motor-driven applications. And, finally, safety practices are paramount when working with electricity. Always de-energize circuits before working on them. Use appropriate personal protective equipment, or PPE, such as gloves, safety glasses, and insulated tools. Follow lockout/tagout procedures to prevent accidental energization of circuits. Be aware of the potential hazards of electricity and take precautions to minimize the risks. Remember that a strong understanding of these electrical engineering concepts, combined with adherence to safety practices, is essential for success in the field.